high, the next we would like to test A and B. Mostly we want to test B, the slope of the regression line. So it's useful to see if the slope is significantly different from 0, because the B has some scientific meaning. For example, that when you increase the calorie intake, does that really increase the weight growth or something like that? So often we want to see if the B is significantly positive or negative. And here we introduce the test statistic and how to test the A and B. So suppose that the epsilon follows normal, the 0 sigma square. So we need the specific assumption about the distribution of epsilon, and the epsilon i's are IID, independent and identically distributed. Then the T sub A hat, this statistic follows the T distribution with degrees of freedom n-2. Here, the n is the sample size, number of observations, and 2 is actually the number of parameters. So we have the A and B. So we have 2 parameters. So T distribution with df n-2. And TA is what? The T sub A hat is defined as the A hat minus A. So A is the true parameter. A hat is estimated parameter, and divided by the standard error of A hat. And the standard error of A hat is obtained by the matrix, the variance of beta hat. You have seen that we got the variance of A hat on a 1-1 entry of the variance of beta hat, and we take square root. So if this quantity, the T sub A hat, is very large or very small, I mean the very large negative number, then it's unusual. So that we reject the hypothesis that the true parameter is A. So we have the same property for B. So T sub B hat is defined by B hat minus B over SE B hat, and B is the true B. And this follows the T distribution with n-2 again. So if, for example, we would like to test the B is equal to 0, this is null hypothesis, and we want to test this against B is not equal to 0. Then the distribution, the TB hat, this is equal to B hat minus 0 divided by standard error of B hat. And if this realization is extreme under this, the T sub n-2 distribution, to be exact, if we use the 5% significance level, if total area of this is equal to 5%, and if our test statistic T hat, TB hat falls in this range, we reject null hypothesis. Otherwise, we accept null hypothesis. I mean, we do not reject null hypothesis. So this is rejection region. And also this is rejection region. And the boundary is not included in the rejection region. So this is how to test the hypothesis such as B is equal to 0, or even B is equal to 1, or and so on. So actually this information is included in the summary of our LM model. So remember that we regressed the price on square footage for condominium data, and we name, so LM of price parenthesis square feet, then we name it as LM1. Then the summary of LM1 includes all information. So you can see hat, and this is B hat, and this is standard error of A hat, and this is standard error of B hat. And this is hypothesis that B is equal to 0. So basically, okay, so B hat divided by standard error of B hat. So this is, okay, so this ratio is equal to this, and 6.198. And 6.198 is pretty extreme value under T distribution with df46. Actually, we have 48 observations, and we have 2 parameters in the model. So we have the 46 degrees of freedom. So t distribution with df46 is almost similar to normal distribution. So normal distribution, you can see plus minus 2 covers 95% of the case. So you can see that the positive 6.198 is very large value. So p-value for this test is 1.46 times 10 to the power negative 7. So it's highly significant. So certainly the square footage affects the price of the condominium. Yeah. So here, the standard error, for example, the standard error, the 0.0399. So this is calculated by the square root of the variance of b hat. That is the 2-2 entry of the variance of beta hat matrix. Yeah, so you can see that b hat is significantly different from 0. And also you can say that this a hat is has the very small p-value. So it's significantly different from 0. So this is how to test the coefficient A and coefficient B.